So now, what are the regularity metrics that are available for us to utilize in the studies that we do? And how would you quantify this? So if you can imagine, you have this individual who has this raster plot, clearly has low sleep regularity. How would you create a quantitative measure to quantify this? And there's a multiple number of ways to do it. You can, for instance, calculate the variability in the sleep onset or the sleep offset, what time you wake up. Or you can incorporate sleep midpoint, which is the midpoint between the sleep onset and the time you wake up. Or you could do actually standard deviation or variability in sleep duration from day after day. How about these wake periods? Obviously, the fact that you have broken up or fragmented sleep should play a factor in your regularity too. So, how do you incorporate that? And then there is the weekend versus the weekday effect as well. People tend to sleep longer and later in weekends compared to the weekdays. So, how do you incorporate that in your regularity metric? So the first one that is probably the oldest one around and probably the easiest to interpret is standard deviation. And in this case, this shows an example of the standard deviation of mid sleep. And the idea is that you identify the mean average of the mid sleep across all the sleep periods that you have. And then you calculate the deviation from each night from this mean. So this creates this standard deviation. So it makes sense that this just means literally the statistical dispersion around the mean across multiple days. Now, you can use standard deviation to multiple daily values. You can apply this not only to mid sleep, but you could do standard deviation of sleep onset and also standard deviation of offset. And you could do the standard deviation for the duration of the night. So you could use that as a marker as well. So naturally, a low standard deviation value means more regularity. And in order to do this in your study, you could just simply use diaries, although it's probably easier just to use actigraphy so that your study participants don't have to go through the labor of filling this out on a daily basis. The issues or the properties with standard deviation is that it is insensitive to day order. You could mix this up entirely and you would get the same standard deviation value. And it's insensitive to naps or fragmentation, right? So if you have breaks where you're waking up in the middle of the night here, this value is not going to take that into consideration. I'm going to talk a little bit about this later. So why is standard deviation itself important? And this is, as I mentioned, it is probably the oldest sleep regularity measure out there. And as a result, there's decent amount of literature evaluating the importance of this measure in a number of clinical outcomes. This comes from that NSF consensus statement. They drew out a figure here, and this took from the data from the MESA study again, and they focused on two clinical outcomes: metabolic syndrome, cardiovascular disease. And within each of these clinical outcomes, they focused on sleep onset, standard deviation, and sleep duration standard deviation. And so they did this for both. And simultaneously, they also evaluated the proportional risk estimates for each additional hour of standard deviation for both metrics. And what they found out was that for each 1 hour of sleep onset standard deviation would increase your risk of metabolic syndrome by 23%. For cardiovascular disease events, for each additional hour of sleep onset standard deviation, you increase your risk of cardiovascular disease events by 18%. So not insignificant. This is pretty important stuff. The other measure that's out there is called interdaily stability. The idea behind this is it quantifies the overall variability in time signal after averaging across days rather than quantifying how rapidly sleep patterns change between consecutive days. So Actually, this came from the actigraphy world. They take actigraph or activity counts. And what you can do is after obtaining data, after many days, you obtain a mean activity level, which is demonstrated here on the bottom. And then for each day, you calculate the deviation of the values from this mean value. So it assesses the stability of this 24-hour rest activity rhythm on each day compared to this average 24-hour pattern. And it has a scale or scoring from 0 to 1, 1 meaning that has the highest regularity. Now, because you are getting such continuous granular data, you cannot just use a diary in order to do this measurement. You have to use actigraphy. And in the literature, it appears that most of the time they use 30-second or 1-minute epochs. The property of this is that, again, it is insensitive to day order. So you could shift around and mix around these days and you still get the same results. But the difference compared to the standard deviation is that since you're getting such granular data, you're applying it to the whole day and can incorporate thus naps and fragmentation. So it will incorporate that in the calculation. And for whatever reason, interdaily stability in the literature has been linked to rhythmicity because in order for the interdaily stability to have a substantial number, it needs alternating states. So if you have high interdaily stability, suggesting that you have an element of rhythmicity in there as well. As it turns out, I was looking through the literature. There doesn't seem to be as many studies that incorporate intradaily stability as a proxy for sleep regularity. But there's a study that was published in 2021. It had 3 groups: healthy controls, insomnia, and post traumatic stress disorder patients. They measured intradaily stability. Since intradaily stability, the higher means that you're more stable. And you can see that healthy controls had more sleep regularity compared to the insomnia patients and the PTSD patients. And this was statistically significant compared to the other 2 conditions. The third measure is the social jet lag index. This one I think is much easier to understand and interpret. It's basically finding the average, oftentimes the mid sleep time during the weekdays and comparing the mid sleep time during the free days, which is often the weekend times. And then what you're doing is you're just taking the difference between these 2 mid times. The social jet lag index is basically a mismatch in sleep timing between socially constrained days, which could be school or work, versus your free days. And again, low value indicates high regularity, and how you do this can be done through a number of ways. You can incorporate just questionnaires. A number of studies have used questionnaires just to derive the social jet lag index. Some have used diaries, others have used actigraphy. The property of this is that this is at a weekly time scale compared to the others, which is at a daily time scale. Like the other 2, this is insensitive to day order. So you can mix things up. You can mix up the work days. Obviously, you can't mix between the work days and the free days themselves, but within the work days, if you mix it up, or within the free days, if you mix it up, you still get the same results. And it does not incorporate naps or fragmentation. A good study that shows the relevance of the social jet lag index was published in Sleep in 2023. This incorporated a large longitudinal survey in Czech Republic, more than 5,000 individuals who filled out a Munich chronotype questionnaire, but they also got blood lipid panel testing done. And what this study found that as you age, your social jet lag tends to decrease. They also found that those individuals who are night owls tend to have higher social jet lag index compared to the larks. And I think this makes sense. Those people who tend to stay up late have to wake up early in the morning to go to work or sleep. That's not going according to their natural rhythm. But then as a result of that, they accumulate sleep debt, which needs to be recovered during the weekend. The importance of this social jet lag index was seen in this blood cholesterol level. Those who had high social jet lag index tended to have higher total cholesterol levels and LDL levels. And this was true in both men and women. And it was statistically significant. But again, social jet lag is something of a mixed bag, in my opinion, because a high social jet lag index may actually be a good thing because that indicates that you're correcting your sleep debt during the weekend. So if you're worried about sleep duration, if you're saying that, you're not getting enough sleep during the weekdays, then the weekends become a time for you to catch up. And that would be represented with a high social jet lag index. However, a high SGAI also indicates that your sleep is more irregular. And as we've seen, that is bad too. So it's a little bit of mixed bag, but I think you'll have to interpret it the way you want to by incorporating other measures. This is the way that Dr. Fischer sort of organizes this is that the way you could get sleep regularity is based on the data that's processed. A single time point is used for standard deviation and social jet lag index. You could use a diary, maybe a questionnaire to get to this. But if you're incorporating a whole day where you're incorporating naps and fragmentation, you need actigraphy types of data. And so interdaily stability would require actigraphy. The thing is, these three measures that I've mentioned don't really take into consideration the order of the events, as I've mentioned. But as you know, circadian rhythms have an inherent inertia. So it's unlikely to change dramatically from one day to the next. So I think it's reasonable then to assume that significant differences in sleep and behavior from one day to the next would be more likely to be discordant with your natural rhythms. And for this reason, several regularity metrics were designed to assess consecutive changes in sleep patterns, so one day to the next. And this one is the Sleep Regularity Index that I talked a lot about. This is the one that spurred a lot of interest in sleep regularity. This is the one that was incorporated in a lot of the large epidemiological studies, such as the MESA and UK Biobank, and associated with many of the clinical outcome measures. A sleep regularity index, it's simply just the probability of being in the same state, sleep and wake at any 2 points, 24 hours apart. And so what you do is you just take your sleep wake classification for one day, let's say Thursday, and then compare it to the following day, Friday. And then you use this method to calculate the difference between the two. And then you do the next same thing for the following 2 days with the overlap, obviously, with Friday. And then you keep on doing this. And ultimately, you get an average, which then generates a result called the Sleep Regularity Index. And this regularity index is this complex formula which enables you to get a scale from 0 to 100, high meaning that it has high regularity. Because this data requires such granular, almost every 30 seconds to every minute type of data for sleep wake classification, it requires the use of actigraphy. You cannot use questionnaires for this. And this actigraphy should have a sleep wake classification in order for us to enter this into the formula. The property for this SRI is that it's sensitive to the day order, as I mentioned. It incorporates the whole day, so it does incorporate naps and fragmentation. The results, the value is a little less intuitive than, let's just say, the social jet lag index, but it is being increasingly used in large cohorts. And thankfully, there had been large population level studies to get an idea of what the population level pattern of the SRI score is. And so this was data obtained from the UK Biobank. They took 61,000 individuals, again, wearing the actigraph for 1 week, and they were able to identify that the median is around a score of around 82 or so. And then it seems to be heavy tailed on the left. And so not too many people with very low scores. I guess a predominant number are in the 70 to 90 range. And so the breakdown is shown here. And the final measure of sleep regularity is the composite phase deviation developed by Fischer. And this is a combination of irregularity and mistiming. And so this one incorporates sleep timing in addition to sleep irregularity. And what Dr. Fisher did was she identified a person's chronotype. It is actually a not so straightforward calculation to figure out a person's chronotype, and then had figure out from day to day how far apart were you from this chronotype, like your natural predisposition, and then use that as a sort of a value, which is the delta CT for each night, and then also calculated the difference in the mid sleep from day to day. So you had both the deviation from your inherent rhythm, but also deviation from night after night. And then so you get these two vectors, which is represented here, y here from the day to day difference and the change from the chronotype. And you could create this vector length. And if you have multiple days, you start to get this pattern. And then you calculate basically the average magnitude to get the CPT value. A low value indicates increased regularity. The way you do this can be because it's a single time scale as opposed to the granular actigraphy, like minute to minute data. You can do diaries and questionnaires, but I think it's probably easier to incorporate into actigraphy. The property of this is that it's sensitive to day order. It's insensitive to naps and fragmentation because it's a single a day value. It needs chronotype estimation, which makes it a little more complex. So this is just a study that was done by Dr. Fisher when she was at Harvard. She measured US college students, about 220. They wore the motion logger for 30 days. They filled out daily questionnaires and diaries. So the actigraphy determines the time of sleep. The students on a daily basis had to describe their well-being and also describe when their first social event was. What Dr. Fisher did was calculate the composite phase deviation for sleep, but also the composite phase deviation for the first social event. So I think what's interesting is that a lot of these irregularity measures can also be applied not only to sleep, but to, let's just say, the first diet, first social event, when you first exercise. So it actually has a lot of diverse use cases. And interestingly, when she broke down this graph between the composite phase deviation of sleep with the composite deviation of the first social activity, she found these four clusters, and she found the cluster four, the students with both irregular sleep and irregular first event, which meaning like first class, first time they're meeting or whatever. This cluster had worse well-being. They were more apt to be sad and more stressed out compared to those who had one or the other. So the combination of irregularity, both sleep and event scheduling, were important. And so this is the way we sort of break it down. If you are looking at single time points, you look at standard deviation or compound phase deviation. This requires just the diary. If you want the whole day, which requires granular information, you use the interdaily stability or the sleep regularity index. These top values do not care about the day order. So that's why it has more of a global sort of relationship. These bottom ones care about the subsequent ordering. So the consecutive ordering. And so if you are looking at that, then you want to look at the bottom two. Now, the question is how many days is needed in order to get a good estimate of these values? This was again done by Fisher in 2021 while she was at Harvard. She created a simulated data set with a known true regularity over a full month, then randomly sampled shorter windows, like let's say every two, like for 2, 3, or 7 days, then calculated the regularity metric of this, and then compared that result compared to what is the known true gold standard. And what she found out was for standard deviation and interdaily stability, you need about 10 days of data to get a good enough estimate, while sleep regularity was surprisingly quite stable. So you only need, as little as 3 days, but ideally 7 days of data to get a good estimate as sleep regularity index. And maybe this is why the SRI was so useful in these large epidemiological studies because if you recall, the UK Biobank only used 1 week of actigraphy data. And so for that reason, SRI was a good measure for that. The other thing that she found out, though, is that in terms of the 95% confidence interval, for whatever reason, SRI and CPD had larger confidence intervals. And what she required was that while it was stable for within an individual, it tended to be a lot more variable across individuals. So I would guess that at least there's a greater interpersonal variability that you need to consider. So if you are going to incorporate SRI, 7 days are going to be sufficient, but you will probably need a larger sample size to account for the interpersonal variability. And this is just a nice summary of how to choose what marker you're going to use. If you have a type of data that has some limited data, like a lot of missing information, use the daily metrics like standard deviation or CPD. If it's not limited, but you're worried about fragmentation, you need whole signals like Interdaily or SRI scores, or if you're not, then CPD and SRI scores. And again, to consider the importance of study length. So the more days of it is the standard deviation in interdaily stability. And you need to consider the sample size as well. So you can look this up in our publication to get this publication. So this is the summary table that I put together here. Feel free to take a screenshot of this. These are the 5 metrics, the types of data that needs to be acquired to do this. The ones that are single measurements in a day are the standard deviation, social jet lag, and maybe CBT can just rely on diaries or questionnaires, but it's probably best to incorporate actigraphy in all of them. And then you need to consider the number of days and also the sample sizes in order to figure out which of these measures would be best for you.